Well, now we're going to start talking about, okay, some financial applications. That is, we're going to start putting some, taking a look at how we look at how we incorporate logs and exponents into an application. We're going to start with one with compound interest. We'll start with simple interest first, okay? So let's suppose you put $1,000 in the bank, which is offering 5%, which you're never going to get today. But for calculation purposes, we're going to keep it at this ideally. Okay, so you invest $1,000 at 5% for 3 years. So what's your return? Well, okay, most people have already been exposed to a simple interest formula: principal times rate times time. Okay, that being the case, principal 1,000 times the rate 0.05. Make sure you put that as a decimal value. For 3 years, $150. Now that's your interest. Let's not forget you had $1,000 that you started out with. Okay, so in total, you're going to get back $1,150. Okay, after 3 years, that's $1,000 plus $150 in interest. Okay, now that's the simple interest. Okay, so this here's a uh, here's a uh, an equation which we can use. Okay, so the interest, of course, is principal times rate times time. So uh, there is principal times rate times time plus the present plus whatever you invest initially as the principal. Okay, S is the amount you have at the end of the whatever period of time you're talking about. So looking at this algebraically, we can see that P is common, so we can pull that out. We got P times the quantity, 1 plus R, the rate times time. So that's your simple interest formula. Now let's see what we do with compound interest. Now, compound interest means interest on your interest. Okay? So, in other words, at the end of the first year, you have $50, but then you collect interest on that plus your principal. So, we're going to see how that works. Okay? So, let's allege that uh, S1 is the amount in your account after 1 year. So, it's basically just this formula that we just demonstrated up here, okay, with the rate of 5% for 1 year. So there it is, 1,050. But now after the second year, you're going to earn, okay, interest on that $50, or you should say that we start out with 1,050. So you start out with 1,050 times the 1.05, so you have 1,102.50. Now after the third year, you of course got, now your start is 1102.50 times the rate of 1.05, so that gives you 1157.63. So as you can see, it's slightly better, $7.63, better than the simple interest. Okay, so so we look at this a little bit more mathematically. Okay, so let's see what the progression is. We're saying that the interest after 1 year is or the amount after 1 year is S1, and that's determined by your principal times uh, 1 plus your rate. Okay, so now that is becoming how much you have at S1, and now that earns the interest. So you have S2 is the amount you have after the first year, S1 times 1 plus R, but then S sub 1 by substitution comes back up here. So you have principal times 1 plus rate times itself. So it's P times 1 plus R, the quantity squared. And if, again, now if you go into the third year, as we saw up here, is the amount you had after the second year, which is S sub 2, times the 1 plus the rate. But after the S sub 2, we found we have principal times 1 plus rate to the second power, and then times another 1 plus rate. So it's principal times 1 plus the rate to the third power. So if we generalize this, we could see that our compound interest formula is as stated here. Uh, the amount that you have in your account after T years is principal times 1 plus the rate to the power T. Okay? Let's look at some example problems. Okay? Now, let's say we wanted to determine how long it takes you to double your investment at 5%. So we have now this formula, okay, and we say this compounded annually. So we have the formula here. S is equal to P times 1 plus R to T. But the amount you want is twice your principal. So therefore your S becomes twice your principal, or 2P. So we come up to the equation here. 2P equals P times 1 plus R to the power T. As you can see, we can cancel out P on both sides, and so in fact say that the time required to double is independent of the amount that you invest, okay, of the principal. So there you have it. Now that becomes a problem, which what we're trying to do is solve for T. All right, we assume we have some kind of fixed R. We're going to work on it generally for now as R, and we want to solve for T. Well, T is the unknown, which is an exponent. So usually what we've found up to this point, solving equations of that variety require us to take the log, and we're just going to take the natural log of both sides. So take natural log of both sides, then we invoke the power rule, and we have here that time is the natural log of 2 divided by the natural log of 1 plus R, where the rate is, in this case, 0.05. Okay, so there we have it. And so at 5%, you're going to double your money, regardless of how much you put in 14 years, 14.2 years, okay? What if we say, how long will it take to triple your money at 6.25%? Well, okay, again, the amount of money is independent, okay? So that doesn't even enter in. So we're going to come back up here, and we're just going to say, we want 3P, so the P is going to drop out. We're going to come down to here. All things being the same, it's just going to be the log of 3 divided by the log of 1 plus the rate. So that being the case, we have the natural log of 3 over the natural log of 1.0625, which is 6.25%. So it looks like 18 years to triple your money at that rate of 6.25%. Okay, so we're gonna stop it here and talk about the in the next video about compounding at a more frequent rate rather than annually, maybe semi-annually, quarterly, monthly, daily, hourly, minutely. Okay, so that'll be in the next video. All right, so we'll watch that one then.